Why does the brain look the way it does? Can the way the brain folds determine how you think? If you look at the brains of different animals, you'll see a pattern. The small brain of, say, a mouse or a hedgehog is very flat and smooth, but the larger brains of more developed animals, like monkeys and humans, have lots of wrinkles and folds. Now, before you think that we're the smartest animal on the planet, keep in mind that the dolphin actually has the most wrinkled brain. What's interesting is that the way the brain wrinkles and folds follows the same laws of physics that describe how the Earth's crust wrinkles and folds. You can use the same equations to describe what's going on. Your brain didn't always look the way it does now. When you're in the womb, your brain starts out small and flat without any wrinkles. Then, around week 22, your brain starts to undergo massive growth. The cells in your brain divide to make more cells, mainly nerve cells. During development, all the nerve cells arrange themselves in a very special pattern, with the cell bodies in the outer layer around the brain and all the cables inside. Scientists call the outer processing layer gray matter and the interconnecting core white matter. When the cells start to form connections with one another, the outer gray matter layer grows so much it doesn't know where to go, so it starts to fold. Scientists believe that this is an advantage because it allows the brain to maximize the number of processing units while minimizing the distance that the signals have to travel between them. What's exciting is that you can model and predict the process of folding with mechanics equations. Mechanics is the study of forces and force equilibrium. For example, mechanics can show that the folding depends on the thickness of the outer gray matter layer and on the difference in stiffness between gray and white matter. It's like folding a piece of paper. The thicker the paper, the harder it is to crumple. Understanding how the brain folds can have really important applications in medicine. For example, it could help us diagnose certain brain diseases or conditions. Studies have found that brain folding may be related to the degree of autism in kids. When scanning the brains of healthy and autistic identical twins, scientists observed that their folding patterns are different in certain regions of the brain. This means that you could use these differences in folding as early indicators for particular forms of autism. Early detection would help you treat autism very early in life, and the earlier you treat it, the more effective the therapy will be. Similar differences in how the brain folds have been observed in cases of schizophrenia. The fascinating idea, once you understand all of this, is can we manipulate the mechanical environment to change the brain? If we can manipulate the folding pattern of the brain early after birth or even later in adulthood, can we affect the behavior and function of the brain to correct certain conditions? Our bodies are amazing biological systems that respond and adapt to forces from the environment. By applying engineering principles and mathematical tools, we can better understand why our bodies develop the way they do, allowing us to diagnose and treat medical conditions in new and exciting ways.